So in order to understand plate tectonics, you also need to understand what are the forces that drive plate tectonics. So one of the current ongoing hypotheses, and the one that more scientists are currently leaning towards as the driving motion for plate tectonics, is that of convection in the mantle and in the crust. So convection, as some of you may know, is one of the heat transfer mechanisms that there are. Conduction, convection, and radiation are the main three, if you're curious. All of you may be familiar with convection, for example, if you have had or have seen a lava lamp at work, or if, for example, you understand the process of water being boiled. So we'll use this last example first. So for convection to have the potential to take place, the first thing needed is a heat source. In this case, for the water boiling, the heat source is going to be the electric stove below the pot of the water that's boiling. So before we turn the stove on, all of the water is at the same temperature. As soon as we turn the stove on, the water will start to heat up. But the heating up is not uniform. So only the particles that are closer to the heat source will start to heat up first. Before I continue with this example, I just want to remind you the equation for density. So the density is going to be equal to mass over volume, right? So let me see if I can write this stuff. Okay. Density is equal to mass over volume. Okay, forgive my handwriting with this, is not very straightforward. So given this formula, if your mass increases but your volume remains constant, right? Or sorry, yeah, if your mass increases, so a bigger M, but your volume remains constant, overall the density will increase, right? So the numerator increasing makes the overall result bigger. So that's gonna turn out to be a bigger density if your mass increases. Conversely, however, if your mass is the same but your volume increases, so you have a much bigger volume, your density will decrease, right? If the denominator decreases, the result will be a smaller one. Okay, so hopefully that is straightforward for now. That makes sense. And again, recall this for the following bit. So also remember that things that are less dense rise above things that are more dense. Okay, so less dense things, for example, like oil or things like ice cubes, will rise above things that are more dense, like water, in either of those cases, right? So for example, again, when you do have ice cubes in a glass of water, those ice cubes are in the top part of the water. They rise above it, or not necessarily above it, but on the top part, because they are less dense. Okay, so now let's think again of the following scenario. You are going to hike on a hot summer day. When you first start your hike, your body is still pretty cool, since you are, for example, let's say inside your car where there's a lot of AC, and so your body's still cool. But as you start hiking, you get out of your car and you start hiking, you start getting hotter and hotter. And your body, as you're hiking, starts showing signs of getting hot. So you're gonna probably start showing things like fatter fingers and wider ankles. And overall, your skin is gonna get a little bit puffier. So given this may be a little bit because you're dehydrated, but most of it is because those signs in your body are showing that overall you're looking more voluminous. You are adding volume to yourself, to your body. So now what you're doing is really you're spreading your weight, which hasn't changed, over a larger volume, because you are, you look fatter even though you weigh the same, which overall makes you less dense. Okay? Again, your mass, which is your weight, stays the same, but you're increasing your volume by getting puffier and puffier, so you're overall a little less dense. Okay. So the same thing really giving all of those things that I just mentioned, is happening to the particles of water that are getting hot near the heat source over here. These particles are expanding as they're getting hot, and as they expand in volume, but they remain constant in mass, they become less dense. So they consequently, as they get less dense, will rise towards the surface, right? And they will displace the colder and denser particles that are at the surface. They will rise above them, the colder, denser ones will be below and get closer and closer to that heat source. So now those colder, denser particles will sink and be closer to the heat source, where they will warm up, expand, rise, and then displace the colder and denser particles that have now been cooled, that were nearer the surface, which is the cooling source in this case. And so the cycle continues on and on. You get warming, expanding, rising, displacing of colder ones which drop below, sink, get warm, rise, expand, so on and so forth. Okay, so that's how convection occurs. And the same thing is going to happen in the example of the lava lamp, right? Except that in this case, it's a little bit easier to visualize for us, since the particles are solid or relatively molten, I suppose. It's easier for us to visualize the material as it becomes less dense and rises, and then as the denser ones actually start sinking towards the heat source, which is this bottom part of the lamp. So convection is thought to be the driving mechanism for plate tectonics on our planet. In our case, in the planet I should say, the heat source conveniently also mostly at the bottom or closer to the center of the Earth is going to be the energy that is released from chemical reactions that take place when there is radioactive decay. So radioactive decay is basically having an unstable form of an element that is decaying or turning into a stable form of the same element or a stable form of a different element. So in this case, when it's in a stable form, it will not react. It will stay that way from now on. Every time that you have an unstable element decay, there will be some sort of energy that is released as part of that decay, as part of that change. And that energy that is released is expressed as heat. So it's through this decay that the Earth has started to cool since the formation of the planet, slowly losing energy, if you would, or moving that energy from the decay of those elements towards other places. In this case, again, making the particles nearby them expand, rise, and displace the ones that are more dense above them. And so, because most of the Earth's material is actually below us at depth, much of the radioactive decay comes from below, hence making the heat source typically deeper than near the surface. So hopefully that makes sense. So as the inner parts of the Earth start heating up, so let's say parts over here start heating up, wherever there is radioactive decay going on, the surrounding material becomes again less dense, and it rises above material that was more dense. And so that material that was more dense will start to sink, just like you're seeing in the arrows here on this diagram. So convection really is driving material to move constantly within the Earth's layer that way. Okay, so here I'm going to talk a little bit about seismology and how it was useful for geologists to subdivide the Earth into its different layers. We will talk about seismology in a lot more detail when we cover chapter 3 and earthquakes. So again, if some of it seems confusing, don't worry, we'll cover it in the next chapter. So seismology itself is the study of earthquakes, the study of seismic waves. And it is useful in understanding the internal structure of the Earth because the changes in speed at which the waves travel, or maybe they don't travel at all in certain instances, is a pretty good indicator of large changes to the density and the viscosity of the layers within the Earth. So seismic waves are caused basically by the energy that is released during an earthquake. This energy moves differently through material of different densities. the seismic waves will move faster through solids than they do through liquids, for example, and faster through denser material. And not all seismic waves will actually move through all types of material, so all fluidicity, if you would. Some of them don't move through liquids or gases, some of them do. So if, for example, we see a delay in time when we are expecting to see a seismic wave arrive at a location, if all of the material, say, was uniform, it may mean that it hit a subsection of material that was perhaps less dense, and hence, because of that material was less dense, the seismic wave traveled more slowly through that subsection that we were expecting to be of the same material. Alright, so now we divide seismic waves into two main parts, body waves and surface waves. The former ones travel through the inside of the layers of the Earth, and the latter ones only travel through the near surface. Body waves are then the waves used to point out the subdivisions of Earth's layers, because they actually travel through the Earth. Body waves are themselves subdivided into two different types. We have primary or P waves, as you see here, which travel through like a compression type motion. So you can think of their motion as a slinky that is simply being pulled and pushed. And this allows for them to travel through solids, through liquids, and through gases. And this allows them to travel fast, which is why they are called primary waves, because they arrive first. The second subdivision of body waves are secondary or S waves, which travel as shear motion, so as shear waves. So here you can think of having, for example, a rope attached to a wall, and you're shaking that rope up and down on the other end. So one end attached to the wall, you have the other end, and you're shaking that rope up and down, which causes the rope itself, or the waves in this case, to travel more slowly than if you were just thinking of the compression waves, right? And it only allows them to travel through liquids. It won't allow for, through solids. It won't allow for liquid or through gas travel. So secondary waves travel about 1.7 times slower than primary waves through the same solid material. So again, P waves only travel through P waves travel through solid, liquid, and gas, and they travel faster. S waves travel only through solids, and they travel slower, 1.7 times slower. Okay, sorry about the confusion. Sometimes these names get to you as you're explaining things. Okay, so as an example, let's use the one that is portrayed here on the image on the slide. So an earthquake that occurred in Iceland, we have recording stations for this earthquake in Novaya Zemlya, which is an island in the Arctic Ocean. We have one in Ulaanbaatar, which is in Mongolia. We have a recording station in the Philippines. We have one in Adelaide, which is in Australia. And we have one somewhere in the South Pole. So in the example, the P waves, as you're seeing here, are blue, and then the S waves, as you're seeing here, are red or kind of pinkish. So for just a few observations that we can make. As you can see, the closer recording stations to the earthquake site, the less time that it takes for the waves to get there, right? So earthquake happened in Iceland, and Novaya Zemlya and Ulaanbaatar see the waves arriving at 6 minutes, 11 minutes, 10 minutes, 18 minutes, as opposed to all the way to 19 minutes, for example, here in Adelaide. So that's one observation to make. The less time it takes for the waves to get there if the station is closer to the earthquake site, which is pretty intuitive. You also see, for example, that the S waves don't make it to either of the southernmost two locations. So they don't make it to Adelaide, the S waves being the red ones, right? They don't make it to Adelaide or to our location here in the South Pole, because they would have to go through the liquid outer core. And as you know, S waves don't travel through liquids, so they cannot travel through the outer core, and hence why we don't see them expressed at the Adelaide or the South Pole recording stations.